Good evening. I'm Rahul. I'm PMRF NPTEL TA for the course Analysis and Design Principle for Microwave Antennas. So this is our seventh live problem solving session. So let's start today's session with question number one. Question number one is, what is the primary principle behind Shelkonov's equivalence principle in the electromagnetic theory? Four options are given and we have to select the primary principle behind Shelkonov's equivalence principle. So first we will see what is Shelkonov's equivalence principle is. I hope I am audible, right? If you have any doubt, you can unmute and ask the question. No issues. Am I audible?
Yes, sir.
Okay, thank you. So I hope the question is clear. It's pretty clear question only. It's just asking what is the primary principle behind Shelkonov's equivalence principle. So like our lecture for this week started with this topic itself, which states that so Shelkonov's equivalence principle states that states that the field in a source free region the field in a source free region is uniquely specified by the tangential component of the electric and magnetic field over the boundary. So what it states, Shelkonov's equivalence principle states that the field in a source free region is uniquely specified by the tangential component of the electric and magnetic fields over the boundary. Tangential components of the electric and magnetic fields over the boundary. This principle uses the concept that fields can be represented equivalently by suitable electric and magnetic current densities on an enclosing surface. So I hope this is clear. That's what has been done in these lectures, right? Like say this is a surface which is source free right now, so they can be defined with the tangential component of electric and magnetic field. That's why this F and M was defined, right? Uh, they were nothing but electric and magnetic current densities on the enclosing surface. So now we will move on to the options. So option A is the tangential components of the electric and magnetic field over a boundary can be uniquely determined the field inside the source free region. This is correct. So that's what the principle uses, the concept that fields can be represented equivalently by suitable electric and magnetic current densities on an enclosing surface. So using those electric and magnetic current densities, we find out E and H over a far field. So that's what has been done for the slot antennas, and the same principle was used for microstrip antennas also. So option A is correct. The tangential components of the electric and magnetic fields over a boundary can be uniquely determined by the field inside a source free region. Option B is the normal components. So the option B is not correct. Only the electric field over a boundary is required to determine the field inside the source free region. No, not that's not what the principle behind Shalkinov equivalence principle. And option D is only magnetic field. Or no, that is also not correct. So option A is the correct one. I hope this is clear. Now we will move on to question number 2. A Z-directed electric current source is located near an infinite ground plane placed in the XZ plane. Then in the far zone from the source, what will happen? 4 options are given. The radiated field will be of TEM type, the radiated field will be of TE type, and the radiated field will be of TM type. And option D is there will be no radiation from the source. So what the question is asking is, there is a Z directed, let's say this is our Cartesian coordinate x, y, z, and then there is a Z directed current source, electric current source, which is located near an infinite ground plane. Let's say there is an infinite ground plane on this XZ plane, and then there is a current source along the Z axis. So if we but we know that this infinite ground plane will act as a perfect electrical conductor. So with the image theory, we can state that there will be an opposing current also will be flowing. So there will be no radiation from the source. So in question 2, we know that the infinite ground plane can be considered as a perfect electric conductor PEC, an electric source parallel to PEC parallel to the PEC could not produce an electric field as an electric current of equal magnitude in opposite direction will be induced to satisfy the boundary conditions also there will be no radiation from the source. So now if we match the options, then the option D is correct. I hope question 2 is clear. If you have any doubt, please let me know. If it is clear, then we will move on to question number 3. In question 3, a rectangular waveguide of dimension A, which is 0.9 millimeters, and B is 0.4 millimeter, is mounted on an infinite ground plane at z is equals to 0. We have to determine the first null to null beam width in theta pi, where theta pi by 2 plane, if the waveguide is operating at 10 GHz and it has a uniform field distribution over the aperture. Okay, so in this question a waveguide is given which is mounted on an infinite ground plane, so it is kind of a slot, and we have to determine the first null to null beam width in theta pi by 2 plane. I hope the question is clear. So in question 3, a waveguide which is operating at 10 GHz is given and it is mounted on an infinite plane. So from this frequency we can find out the wavelength. Which comes out to be 0.03 meters, and this rectangular waveguide A and B are given. A is 0.9 millimeters and B is 0.4 millimeters. And be careful while you're writing, while you're solving the question, because there is a pretty high chance that there is a option which assumes them as 0.9 meter and 0.4 meter. So just take care of the units while you are solving. So these are given in millimeters. So first convert them to meter. So in the problem we have to find out the first null to null beam width, which we have already seen in the problems that in the lectures. The formula for this is 2 sine inverse lambda by b. So 2 sine inverse, where lambda is 0.03 and b is 0.0004 in meters. So when we solve this, it comes out to be 2 sine inverse 750. Now if we look, because we know that the sine or sinusoidal functions are in the range -1 to 1, but here the sine inverse is going up to 750. So this argument of sinusoid cannot be greater than unity, right? Argument of, so it cannot be greater than unity. It's not possible. It's 750 is not possible. It has to be less than 1 sine inverse, because for any angle sine, for any angle it cannot be greater than 1. So that's why, therefore, nulls does not exist in visible region. So now we'll see the options. So option C is correct. I hope this question is clear. If you have any doubt in this, please let me know. If this is clear, we will move on to next problem, which is question 4. The maximum effective aperture of a waveguide aperture of dimension A and B in an infinite ground plane is. The maximum effective aperture of a waveguide aperture of dimensions A and B in an infinite ground plane is. So we have seen in, I think, first lecture of this week or second lecture of this week, that the aperture efficiency of a slot. So it's a slot only because that waveguide aperture is on an infinite ground plane. Suppose this is the aperture and it's surrounded by the infinite ground plane, so it is acting like a slot. So, and we have seen that the aperture efficiency is 100%. That means AE is equals to A physical. So in case a rectangular waveguide, the area is AB. Effective aperture will be same as the physical aperture. I will note it down here. Question 4. The maximum effective aperture of a waveguide aperture in an infinite ground plane is area of the aperture. That is A into B. So if we match the options, so the correct option is A. I hope question 4 is clear. If you have any doubt in this, please let me know. If this is clear, we will move on to question number 5. So here for question 5, 6 and 7 there is a common data. So we have to solve question 5, 6 and 7 for a rectangular aperture having dimensions A is 4 lambda and B is 3 lambda. It's mounted on an infinite ground plane. First we have to find directivity of the aperture. In question 6 we have to find the E plane null to null beam width in degrees. And in question 7 the angle at which maximum of the first side lobe occurs in the E plane is. So first we will solve question number 5. Here A is given as 4 lambda, B is given as 3 lambda, and for a rectangular aperture mounted on an infinite ground plane, directivity is given by 4 pi A into B by lambda square. So in the problem A and B are given, which is A is 4 lambda and B is 3 lambda divided by lambda square. So it comes out to be 48 pi, which is 150.7964. But if you see in the options are in decibels, so we'll convert it in dB. So directivity in decibels is 10 log 10, 150.7964, and when we take this logarithm we will get 21.78 decibel. So here if we match with the options, correct option is see 21.78. Now in question 6 we have to find the E-plane null to null beam width in degrees. So in question 6 we have to find the E-plane null to null beam width is given by theta null to null is 114.6 lambda by b. So this formula is already has been derived in the lectures, so I'm not going to derive, I'm going to directly write it, and it's better you guys also remember these formulas for your exam, for your final exam, because those formulas won't be given in the exam, so you have to remember them, and it's better to remember instead of start deriving during the exam, then it will take long time. So b is given as 3 lambda, so 114.6 lambda, and when you solve this you will get 38.2 degrees. So we will match with the options, so correct option is option A, 38.2. I hope question 6 is clear. Now we'll move on to question 7. The angle at which maximum of the first side lobe occurs in the E plane is. So it's asking about the first side lobe angle. Let's say if this is a E field pattern, it doesn't have to be the correct, I'm just drawing one. So we've seen that there is a sinc function involved, x by x, like that was there in the E field distribution, E field pattern in far field. So definitely the side lobe will be there. So it wants us to the maximum at which angle it happens. So this angle we have to find out. I hope the question is clear. So first side lobe is the immediate lobe after the main lobe. So the angle at which maximum of the first side lobe occurs in the E plane is given by theta s is equals to 81.9 into lambda by b. So this formula is for degree in degrees. So 81.9 into 1 by 3, because b is 3 lambda, and when we divide this we will get 27.3 degrees. So the correct option is B, 27.3. I hope question 5, 6 and 7 are clear. If you have any doubt, please let me know. Okay, if they are clear, we will move on to question number. Okay, question 8 is not here. Okay, question number 9. In the analysis of a microstrip, so we will move on to question number 9 then. In the analysis of a microstrip antenna, the effective area A is given as 8 pi square into AP, where AP is the physical area. What does this implies about the aperture efficiency of the antenna? So I hope the question is clear. In the analysis of microstrip antenna, the effective area A is given as 8 by pi square into AP, where AP is the physical area. What does this implies about the aperture efficiency of the antenna? The aperture efficiency is always greater than 1. The aperture efficiency is always less than 1 or equals to 1, and option D is aperture efficiency is not related to this ratio. So we know that aperture efficiency is the ratio of physical to the effective. Okay, I will write this down. So the aperture efficiency is the ratio of the effective area to the physical area. Since effective area for the microstrip antenna is given by 8 by pi square into AP, this implies that the aperture efficiency is by pi square, because I can take this on this left hand side. AE by AP is 8 by pi square, which is approximately equal to 0.81. Therefore the aperture efficiency is less than 1. So correct option here is option C. B is correct. The aperture efficiency is less than 1 for a microstrip antenna. I hope question 9th is clear. Now we will move on to question number 10. Question 10. Which of the following is true for an electric conductor equivalent? So which of the following is true for an electric conductor equivalent? So here electric current and magnetic current densities are given. For and we have to tell which is the correct option for a electric conductor equivalent. So in question 10, 4 options are given and the equivalent surface currents are JS and MS radiates field. So the equivalent surface current JS and MS radiates fields H and E respectively. Like this, JS electric current density radiates magnetic field, and magnetic current density radiates electric field respectively. the conditions for the electric conductor equivalent are Js is n cross h is 0 and ms is minus n cross e. So this is the condition and we will match with the options. So if we see option D is correct, where Js is n cross h is 0 and ms is minus n cross e. So option D is correct. I hope this question is clear. If you have any doubt in this, please let me know, or you can refer to the first lecture of this week. It has been explained clearly there. Now we will move on to question number 11. So I've skipped one question here about that question was basically asking that two statements were given. Statement 1 was that if we put a high dielectric substrate in a microstrip antenna, the size of that antenna will reduce. And then there is statement 2 was the high dielectric constant results in a shorter effective wavelength in the substrate. And the options were like different options were there, and one option was there, it was asking statement 2 is correct explanation of statement 1. So I will just write it down here as a note. So I skipped that question, so I will directly explain that here. A higher dielectric constant results in a shorter effective wavelength in the substrate of a microstrip antenna. So a higher dielectric constant results in a shorter effective wavelength in the substrate, which leads to a smaller antenna size for the same resonant frequency. For the same resonant frequency. What does it means is, if you have two, let's say two antennas, microstrip antennas are there, and which has a radiating patch of some this kind of a shape. So both have the same shape of the patch, but a different dimension, and both are radiating at the same frequency. Let's say both are resonating at 434 megahertz, but the only difference is this has a substrate whose let's say dielectric constant is epsilon r is, let's say, 40, and here it has some dielectric it has a substrate which has a dielectric constant of, let's say, 78 or something, so which results in a shorter size. So that's what people are using for microstrip antennas to reduce the size. That's why you can see there can be some small antennas which are radiating at some frequency, but their size is small compared to the frequency that they should be resonating at. So that is because of the high dielectric substrate. So a lot of research has been going on to find out the high dielectric ceramic materials which can be used as a substrate for these antennas. So that's just a small note, I forgot that question here, but that question was basically asking that why the size of the antenna is smaller. So if it has a higher dielectric constant aperture substrate, then the size of the antenna will be smaller, because a high dielectric constant results in a shorter effective wavelength in the substrate. Now we will move on to question number 11. In question number 11, design a rectangular microstrip antenna using a substrate. So here this RT Duroid 5880 is a type of substrate that has been used for designing the microstrip antennas whose dielectric constant is 2.2. So ideally all these available things are their dielectric constant is small only. That's why this research is going on to find out the substrates which has a high dielectric constant. So it will help to reduce the antenna size significantly. Like if you have a substrate whose dielectric constant is, let's say, 90 or 100, so that antenna will be considerably smaller than this antenna which has a substrate of RT Duroid 5880, and the height of that patch is 0.1588 centimeter, and it has to resonate at 10 gigahertz. So design a rectangular microstrip antenna means we have to design a rectangular antenna. That means you have to find out the length and width. Let's say this is the microstrip antenna, this is the feed here, this is the length, and this is width. So we have to find L and W for this. This is the patch of that microstrip antenna, and because of the fringe fields which are emanating from this radiating patch, the effective length will be slightly longer than the actual length, which is, we will denote it as delta L. Delta L. So in this problem, we have to find L and W. That's what designing a microstrip antenna is. Question number 11. The width W of the patch is, so I am directly going to use the formula for a rectangular patch antenna. W is given by C by 2F, where C is the velocity of electromagnetic wave in free space, into 2 divided by epsilon r plus 1. So in the problem, epsilon r is the dielectric constant of the substrate, is given as 2.2, and the width of the patch is 0.1588 centimeter. So W will be, and the frequency is also given in the problem as 10 gigahertz. F is given as 10 gigahertz. So I'm simply writing it as 10 to the power 10 into 2 into 10 to the power 10 divided by 2 divided by 2.2 plus 1. And when we solve this, we will get the width of the patch as one rectangular patch as 1.186 centimeter. Now we have to find the length, and for finding the length, first we need the effective dielectric constant of the patch. Epsilon r effective is given by epsilon r plus 1 divided by 2 plus epsilon r minus 1 divided by 2 into 1 plus 12 times, where h is the height of the patch and w is the width that we find out, the whole power minus 1 by 2. Now we will substitute these values. 2.2 plus 1 divided by 2 plus 2.2 minus 1 divided by 2 into 1 plus 12 into 0. The h is given as 0.1588 and centimeters, and w is 1.186. So I'm not converting any of them into meters because both are in centimeters. So I'm directly writing them as it is, into power minus 1 by 2. So when we solve this, epsilon effective dielectric constant of the patch comes out to be 1.972, and the extended incremental length of the patch, that is at delta L, is given by using this formula we can find delta L by h is equals to 0.412 into epsilon r effective plus 0.3 into w by h plus 0.264 divided by epsilon r effective minus 0.258 into w by h plus 0.8. So for the derivation of these formulas you can refer to the Balani's book in the chapter for microstrip antennas. So when you substitute the values, we will get delta ls, h we will take on the right hand side, 0.1588 into 0.412, epsilon r effective is 1.972 plus 0.3 into w by h, w is 1.186, h is 0.1588 plus 0.264 this divided by 1.972 minus 0.258 into 1.186 divided by 0.1588 plus 0.8, and when we solve this we will get delta ls 0.081 centimeters, and the actual length is given by actual length of the patch is L is C divided by 2F into under root epsilon r effective minus 2 delta L. So C is 3 into 10 to the power 8 divided by 2 into 10 to the power 10 into r effective 1972 minus 2 into 0.081. So L is 0.906 centimeters, and we can also find out the effective length, which is sum of L plus 2 delta L. L effective is L plus 2 times of delta L, which is 0.906 plus 2 times of 0.081, which is 1.068 centimeters. I hope this question is clear. but I will suggest that you follow the lectures. Whatever the topics have been discussed in the lectures, you remember and learn those formulas and only. So I think these formulas for the my rectangular patch is not been discussed. So it's just for your reference and for learning. But if these formulas are not have been derived and discussed in the lectures, you don't need to remember those things. You just have to learn what these are, but no need to learn the remember the things which have not been discussed for the exam I am talking.
Sir, are these formulas important for exam point of view?
Not the microstrip patch one, but rest yes, all of them till question number 10. Yes,
Okay.
but question number 11, I think these formulas for microstrip patch are not discussed in the lectures.
No, sir, it isn't discussed.
Yeah, that's why. So you don't have to remember uh, for question number 11, but rest I think you have to remember because all of them are from the lectures only.
Okay.
Okay. So because all of these questions are provided by the course team only, so till question number 10. So it's better if you go through the questions which I am also discussing. It will be beneficial because these questions are pretty similar to what have been in the assignments. So for the exam, if you solve all the assignment problems plus just look at whatever the problems I have solved, then it will be more than sufficient, I think. If you follow the lectures carefully, questions will be pretty simple. Like their level will be similar to that of the assignment problems. So follow the assignments and the lectures, and if the time is there, you can solve the problems which I have solved. But most
Right, sir.
important is the assignment problems.
Okay, sir.
Okay, for question number 12, this is also about a rectangular patch antenna. So I will give it as a homework. If you want to just learn, you can solve it. It's a solved example problem from chapter 14th, I think, from Balanis. And this is just one example of a slot antenna. So these are the slot antennas which are printed on a metal sheet. Lot of slots are there, so they are acting as an array, and which is mounted on a seeker. That is acting as a seeker for a missile. So that is because they have a very high directivity. So that's why they have been used in a seeker for a missile. So just one example for a practical thing like how these antennas are being used, particularly slot antennas because we don't see them often. Okay, that's all for today's lecture. Thank you.
Thank you, sir.